Thank you for the kind introduction. I appreciate it. So this is a talk I pulled together with Al Guerra to describe our efforts to get to Exascale. The lawyers always have to chime in. This basically says these are forward-looking statements and don't represent reality. So Exascale Challenges, summary here is keeping the system power reasonable. It's amazing that a double-digit megawatt number can be thought of as a reasonable power number for systems, but that's where we're at. We also really need to think and rethink about system resiliency with a target of keeping the machine up for about a week. Beyond that, doesn't really buy you a lot because even at 2 weeks, you haven't bought twice the productivity. But if that drops much below a week, say less than a day, less than a 8-hour working period, then people trying to utilize the machine aren't very productive. You spend more time fixing the problems and that sort of stuff than you do getting useful work out of the machine. And end users are very unhappy. So it goes from less than a shift, very unhappy users, to about a week, very happy users. Beyond that, you're not buying much. So that's the sweet spot we want to aim for. And then because of the levels of parallelism here, there's three scalabilities. There's scalability of the hardware, scalability of the software, the system software, and then the scalability of end user applications. And all of this, as I mentioned, is being driven by the extreme levels of parallelism, and the power is really about moving the data around, either within the processor or between the processor and memory, from node to node. All of that chews up a significant amount of power. So if we're going to achieve that 20 megawatt number up there, we have to focus on data locality. And then with all these levels of parallelism in a machine, we seriously need to focus on programmability. And I'm of the mind that MPI plus X, where X is some kind of SMP parallelism within an MPI task, is the way to go short term, but long term, over the next 10 to 20 years in the exascale era, we really need a new programming paradigm, programming model support. But it will be a long-term transition where both a new programming model and the existing programming model need to coexist and work well on the transitional platforms so that the existing workload can make that transition. And then the memory wall is there, and that amazingly enough started showing up as a bandwidth problem. And depending upon your memory access patterns, that bandwidth problem can turn into a latency problem. And then the next place where that really gets us is the power. Notice I haven't said capacity, right? The memory wall is really about data locality, bandwidth, and latency. So for us, and my title, we want to make sure that this systems approach is provided through the IA ecosystem through multiple partners. So we have been in discussions, as other OEMs and technology providers have been in discussions with the U.S. Department of Energy around an Exascale initiative. And consistently across the industry, we're saying that addressing these challenges is really an order dollars billion, right, effort over a 10-year period of time. It's not a 10 or 20 million dollar 2-year kind of R&D effort. So why is it so difficult? Well, the challenges are over there on the left, and the technology directions are over there on the right. So silicon technology, much to the naysayers' chagrin, is on track. We're fielding 14 nanometer fabs now. I think the recent quarterly announcement, we made said that the yields out of that are not coming up as fast as we'd like, so that's going to take an extra quarter. But basically, we're still on track. We are, transitioning 10 nanometer at the moment from research into fab development. So we don't really see an end to that in this decade, which is good. The memory technology, though, will be a long-term key problem that we have to solve. And I'll spend some time talking about that, which is kind of interesting that a processor design company is talking about memory technology. And systems architecture is key to this scalability and programmability. They go hand in hand, programming the system and the design of that system. So I'll talk a great deal about that. And then algorithms and system software are another factor. So if you're going to make a dent in any of these, and we have to make a dent in all of them for the exascale era to be successful, we have to start working on that pretty soon. So one of the most amazing things that I've had to kind of deeply understand and then try to communicate to the community here is that, if you look at the LINPACK performance, it's really a compound annual growth rate of about 2x every year. And, Moore's law, tells us that on the silicon side, we get, twice the transistors on a die of roughly the same size for roughly the same cost every 18 months. So that translates into a performance CAGR of roughly 2x every 2 years, right? So how is it that the top 500 list gets 2x every year? Well, it's been the brute force aggregation of more processors together, and lately it's also been about getting better performance out of those processors, efficiency. But bottom line is that 2x every 2 years comes from the processor, and the other 2x every 2 years to get you to 2x every year comes from increasing system size. And the doubling rate here is really, to 3 decimal places or 2 decimal places, 2x every year. So the other thing to recognize, this is Sequoia at Livermore as they were building it. That was the K computer, which was #1 on the top 500 list before that. And this is Tahe 1 in China. Jaguar before it, Roadrunner at Los Alamos, and Blue Gene L back at Livermore. And then before that, the Earth Stimulator. So, if you go back in history, the last 12 systems that were #1 over the last 17 years since the ASCII program started, and have all been funded by 3 different governments, China, Japan, and the US, with the numbers down below, which is quite amazing. So it's not like this should be a surprise to anybody that we need long-term, large-scale government funding to help make these technology transitions happen. The other thing that I find quite amazing is if you add up the flops in the top 5 of the top 500 list over time, you get a really large number relative to the rest of the list. And this shows this is one of Eric Strohmeyer's graphs showing the #1 system, what percent of the flops is in that relative to the rest of the list and so forth. through 2, 3, 4, and 5. But if you sum it up over there on the right-hand side, that's 40% of the flops in the top 500 are in the top 5 systems. So this, what that really tells me is that the system size of that top tier, in terms of number of cores and number of processors, meaning multi-node parallelism with an interconnect in between, is at extreme levels. At the other end of the spectrum, and again, there's the Moore's law curve on the left-hand side for processors, doubling the transistors every 18 months. And what's memory doing? Well, memory is also on a Moore's law-like curve, and through the 80s and into 2000, that curve was 4x every 3 years. So basically, they were waiting a generation and then leapfrogging 2 generations in terms of processor development, right? And so roughly that kept up. But then back in the 2000s, a couple of things happened. There was a market shift of memory technology that put more emphasis on flash memory as well as DRAM, siphoning off development resources away from the CAGR for DRAM, and also there was an economic crisis or two in between there, which damaged the profitability of the memory market, limiting again the investment. So the CAGR there has really dropped back to 2x every 3 years. So they've halved their compound annual growth rate. So if you compare the processor with the memory, we're going to get a lot less memory per processor transistor over time. So that's going to hit the B to F ratio in terms of bytes per flop of memory design. So at the highest level, this is the concept that we work with when we're thinking about system technologies at Intel, of a machine with a very large number, 50,000 to 100,000, going to 1 million processors in it, 1 million processors, toward the end of the Exascale decade. And each one of those processors has an integrated piece of the interconnect and some flexible interconnect fabric topology options to pull those together. We don't see each one of those processors talking to the outside world. It'd be way too expensive. And so we move to a hierarchical infrastructure where there are some number of compute nodes that talk to what we call OS nodes with burst buffer, NVRAM there, which then talk to the outside world, creating an N into 1 into the SAN taper, which allows us to control the costs and the complexity and improve the reliability of the system. That SAN there is a high-speed network. Many places that's Ethernet or InfiniBand and other technologies coming down the road there. But that's another full crossbar, fat tree or other topology interconnects of similar technology to what will be inside the machine that will give us high-speed access to login nodes down there at the bottom and also service nodes. Login nodes are the nodes that service end users and are outward-looking, and service nodes service the machine, and those are inward-looking. Both of those are scalable clusters that scale in size and complexity with the size and complexity of the compute partition there on the left-hand side. And then on the right-hand side, there are other resources within a computer center. Now we've moved into where does this thing live within a computational environment, and these things are never standalone systems. In particular, you need a Lustre parallel file system there in an archive, and then other resources like a Viz cluster and other compute resources that would be there from previous generations or capacity clusters or emerging cloud or Hadoop style big data designs that I'll talk about in a few slides as well. So this system design is focused on the end-to-end problem of using a machine to do productive and predictive science and engineering in an environment, in a complex computing environment, all the way down to the scalability of an integrated fabric. So, and that that design is a focus that enables us to make end-user applications productive, end users productive. So the hardware, for reliability reasons, as I've mentioned, needs to be on the replicated, highly replicated unit, which are those C boxes there, and the interconnect be as simple as possible. And it needs to be hierarchical so that the complexity can be abstracted out to a set of OS nodes with burst buffer, right, which can have an order of magnitude or more, two orders of magnitude, fewer of those, and be more complex and still remain scalable. So that talks about the hardware. For the system software, we think a hierarchical function shipping mechanism where most of the OS functions on the compute nodes are actually handled by that OS node over there, allows us to factor and solve an impossible problem of having an operating system and all of the mounted file systems and all the other system services mounted on 100,000 nodes going to 1 million nodes there on the right-hand side. We factor that into two problems. One is a much smaller set of OS nodes, like I said, 1 to 2 orders of magnitude fewer, and then a very simple kernel over there on the compute nodes, which gives end users a real Linux environment. Within that, we need to focus on the applications. And the more I think about this problem, the more convinced I am that we need to move to an era where we're actually talking about asynchronous applications as opposed to the bulk synchronous compute, communicate, and then dump I/O. Compute, communicate, like that require everybody to do everything very synchronously to an asynchronous model. So to enable the hierarchical model, we're currently doing R&D in what we call multi-OS environments, where the runtime system is one that services the application, but it does it very lightweight, bare to the metal kind of environment, where when system calls happen, they go directly to the metal, if it's just read a register, a hardware performance monitor, something like that, communicate across the interconnect, or if it requires a system function, that gets shipped over to a local Linux that's stripped down and made as industrial strength as possible, minimize the daemons, tune for the compute node environment, very specialized, domain-specific kind of OS tuning there. And if it's a local OS function, like fix up the TLBs or create a process or a thread or something, that Linux handles it. But if it's a more global function, like communicate on a socket, do file I/O, job launch, interact with a debugger or whatever, that gets function shipped across the interconnect over to the OS node with the burst buffer in the hierarchical hardware system architecture to an I/O daemon and other daemons on the OS node, no daemons on the left, where it gets serviced by the Linux that's actually running there. So the goal here is to take a shrink wrap binary, HPC binary, that runs on a workstation Linux and plop it on this thing and it still works, right? Now, of course, if you're going to go to a 100,000 node, million way parallelism application, there's hard work to do to scale that application and debug it and all that kind of good stuff. So I don't want to minimize or trivialize the effort here. But what we're saying is that this end user experience is one where there's a machine here that can be used at small scale in the volume space, but also scaled way up to Exascale and the top 5 of the top 500 list and maintain the same end user experience. And this is key to our strategy of extending IA in HPC for Exascale. It's served us quite well. We have all kinds of support in the IO ecosystem. It's quite amazing, actually, for instruction level parallelism, data parallelism, thread parallelism, and cluster process parallelism. And we do it, with serial code at the node level to extract instruction level parallelism and vectorization and so forth. And then we have parallel node level programming model support for arrays and vectorization and data parallel type operations. And then we also have support for multi-node cluster level stuff with multiple versions of MPI and other messaging paradigms available. Now, if you contrast that with the programming model for GPUs, there's basically one box there. It's node level parallelism, that it's data parallel. And that is a pretty small domain, if you will, of programming that limits the usefulness of that approach. Now, thinking about these exascale systems in the context of using them in a data center, there's talking to the cloud folks at Intel and end users. There's quite a bit of overlap of the technologies. They're into scale out, right? The cloud is, and big data is into really scale out, where the network is primarily at the moment Ethernet, but there's a lot of parallelism available in that environment and being exploited, in very similar ways today as HPC was exploited a while back. And it started out basically as batch type operations over there on the left, and then moved to interactive, transaction-oriented kinds of stuff in the middle for business intelligence and data warehousing. And then the predictive multi-level language support in cloud and big data now has transformed the access methodologies for the usage cases on the left there. Now, the amazing thing is the data collection in the cloud is a set of sensors, devices, and end users out there, wandering around with a phone or a tablet or a laptop, needing data. And, we see that driving the infrastructure needs of cloud providers, where I think Diane Bryant was quoted in the head of Data Center Group saying that for every phone, for every 4 phones, there's a server back at the phone company, servicing data for those phones. So even though we kind of say we're already in the phone market because we're supplying all the servers that provide you the data for those phones. And then what's happening on the right-hand side is the information that gets created from those data sources. And how it's used. There's models that are applied to the data that, when you get differentials from the model to the data, you learn something. And also the data informs new models. There's queries just to, get the information out of it in reports. And, again, this is driving a lot of data center growth, that use case for big data. And support of mobile clients and so forth. So but if you look at like there was 2 Nobel Prizes this last year that were announced, one in chemistry and one in physics that were based on and informed by either computational chemistry or the analysis of data coming out of CERN, right? And that's amazing. That's exactly the same model here, streaming data in real time and data analytics, predictive simulation capability over there on the right generating the data. So there's a very large overlap between these two models, and we think a system design such as this with the I/O forwarding mechanism, boy, these fonts got all messed up in translating to a new laptop. But anyway, when we talk about the middle petascale era, hundreds of petaflops that are pre-exascale class systems, we see, in more detail than I had on the previous slide, that they're architected now with a lot of emphasis on bandwidth and capacity of various memories, and in particular, new memory technologies are emerging at scale in these systems, starting with flash. And the places to put flash are obviously on the compute node, on these I/O nodes with burst buffer, or out in the parallel file system. So the pluses and minuses of all of those are that if you put it on the compute node, it's local to every node. You get very fast I/O. You get a lot of capacity there. The problem is it's really expensive, and it kind of craters your MTBF number. So that's probably not a good idea. So I don't show it there. However, if you aggregate it on those OS nodes in 100-to-1 kind of a ratio to the compute nodes, then that kind of balances the network bandwidth to what you can get out of flash devices on those I/O nodes, OS nodes with burst buffer. They're in the middle. And what that allows you to do is to do checkpointing at very high speeds and random I/Os at flash speeds, and then aggregate that I/O and go over a much lower interconnect to the SAN fabric, where you use rotating disks on the back end there, where you trade, make a different trade, you get capacity there at much lower bandwidth. So the burst buffer thing in the middle there is very high bandwidth with low capacity because of the cost, and then that Lustre parallel file system is the capacity, but much slower. So we're working today with a DOE fast forward project in storage and I/O to create burst buffer technology, and also a new access methodology called DAOS for distributed application object store, and I'll talk about that in a few slides. So we really have to get serious about power efficiency. Today, the best machines power efficiency is about 2.5 gigaflops per watt. But that's a factor of 20 where we need to be in terms of 50 gigaflops at an exaflop in 20 megawatts. So, what we can build today, if you max out the interconnect size and people's hundreds of millions of dollars platform budgets, is about 300 petaflops. That's really the scale. So we're in this mid, petaflop pre-exaflop era, and that's around 30 megawatts. That's above, where the target is for Exascale at 20 megawatts, and we're 1/3 of the way to exaflop. So these designs will not support Exascale unless we get very aggressive about developing technologies that save power, and then use the power only where it's needed, and optimize the heck out of the application, the architecture, the fabric, the memory, and the processor to get there. And now we think that this is where we can interact with end user applications and get the applications programmer to tell us what's right. Predicting things will get you only so far along the way. So this, as I mentioned earlier, has to be a focused long-term R&D effort, and we have to do it with other applications besides LIMPAC. So we're rethinking the system-level memory architecture and looking at new emerging memory technologies, new levels of the memory hierarchy. The burst buffer, you can kind of think of as a new level of memory hierarchy. And then we want to minimize the amount of data movement within a processor, between the processor and the memory on a node, and then node to node across the interconnect. And then we need innovative packaging and I/O solutions as well. So a typical DRAM memory die in 2016 will be 8 gigabits and about 100 square millimeters, as always. That's kind of the die size for memory. If you look at the processor floating point unit in that time frame as well, it's way smaller and gets 2 flops per cycle. And even if we made that floating point unit in a core that had other features to it, that was 100 times bigger than that FPU, and about 1 gigabyte per core, which is sort of the low end of what users tell us they want to have as a memory address space for their MPI tasks, and then have 1 MPI task per core. We have 100x more silicon in memory than in processing. So this is not cost balanced at all. Threading, as I mentioned earlier, gets us a way to aggregate more cores and threads to that 1 gigabyte of memory. So now we can make the processors bigger, but we have to have the bandwidth then in that aggregate to support all that thread level parallelism within an MPI task. So we need a new memory architecture, new memory technologies that allow us to go there. So this is a taxonomy of emerging memory technologies. Memory at the highest level breaks down into 2 types of memory: volatile memory that needs to be refreshed and the power needs to be on all the time to keep the data alive, and then non-volatile memory where it doesn't require a refresh and the state remains even if the power is removed and applied again later. Underneath there's very mature technologies in the flash area, both NAND and NOR flash. Intel, in partnership with Micron, makes a lot of that. And then there's prototypical type memories. Memristors is one. Phase change memory is another. And then there's an emerging class, RRAM, nanomechanical, polymer, and molecular type memory technologies that are farther out. So there's the what's available, what's coming, and what we see. So we need to exponentially increase the bandwidth because we're exponentially increasing the number of cores per die, the parallelism within a core, which drives the bandwidth, and we need to exponentially decrease the power to picojoules per bit. Traditional DRAM has been organized in pages, and many pages are activated at any time, and lots of reads and writes happen to keep those pages refreshed, and a small amount of the data, the read data, is actually latched and pulled out of the chip across the memory bus to the processor. So this requires a small number of pins. There is a different way to organize the data here, and the new DRAM architectures that we're advocating are ones where instead of having a lot of open pages, there's one open page at a time, and the read and write and refresh only what is needed, right? And all the data that is read is then transferred to the processor. So now the refresh, the open pages, and the data that's read is all optimized for what is actually used, right? And that allows us to get much better, power ratings per bit read and transferred. downside of it is that it requires a large number of IOs, and we may even have to go to 3D IOs to do that kind of a thing. So that really means that if you're on the other side of a memory bus in a DIMM on the motherboard, that's probably not going to work, because we're definitely pin limited going out of the package. So that led to a partnership with Micron, and I think Micron and the last supercomputer area actually announced a product based on the hybrid memory cube. It's a 3D integrated technology with through silica via to transfer the data, which gives us the 3D pin structure that we were talking about. It starts with a 1 gigabit array for a total of 512 megabytes in a cube, which is non-trivial. But the bandwidth number there is pretty spectacular. It's 128 gigabytes a second, where DDR3 technology on the other end of a memory bus, as opposed to a memory cube that is in the package with the processor, is an order of magnitude less. And oh, by the way, the picojoules per bit is not quite an order of magnitude, but a factor of 8 less than the DRAM as a result of that. So 10x better bandwidth, 10x, roughly 8 to 10x lower picojoules per bit. So this memory technology is one where the memory cube sits in the package with the processor, but is not stacked on top of the processor and is separate. So that's one way to do it. Other ways to do it is to go and be more aggressive with stacking the processor on top of the memory cubes in some way, or stacking the processor spanning multiple DRAM arrays. Both of these are power packaging and cooling type problems, and power packaging and cooling generally is not on a Moore's law and is very expensive. Going to this type of design methodologies has tremendous yield issues associated with it. You have to first yield the DRAM die and the processor die, right? And then you have to yield a stack, right, which is a multiplier. It's not 100%, right? And then you have to yield multiple stacks in a package, right? That's another hit to yield. And then you have to put the processor on top of it, either across multiples or individually over there on the left-hand side, which now takes the processor yield and decreases that in that packaging step. So if you're not careful, really careful in the manufacturing of these kinds of devices, you can go from pretty good, good die on a wafer yield rates to packaged processor yield rates, which drive the cost of that integrated package up by a factor of 10 just on yield considerations alone. And that's one of the major reasons why this technology hasn't just showed up, right? And requires some significant investment to get there. The other thing is that processors today are actually really thin. After they're cut off the die, then they plane them to make them even more thin. And in this thermal environment where you turn it on and you turn it off, it's highly used, it goes idle, there's a lot of expansion and contraction. These chips actually crack. So there's the heat dissipation and retention issues are fundamental and quite difficult as well. So those are all things in triple digits dollars M per generation that you have to deal with if you want to get to this class of technology. So now beyond the DRAM architecture, which I've described here, there are other innovative memory technologies that appear to give us 2 to 10x the capacity per dollar than DRAM, which is great, and we'll need this in order to absorb lots and lots more cores and put it on a stack of memory. If we don't do that, then memory performance is going to drop by a factor of 10 to 20. from current levels, and aggressive threading will be necessary within applications as opposed to modest threading over there on the left-hand side. And the program model changes to focus on threading as opposed to the program model on the left-hand side, which focuses on increased task scaling. So I think the message I'm trying to get across here is that we have a fork in the road between us and 2025. And on the left-hand side there is serious investment to get us over the hump with new memory technologies, and both on the DRAM side and new things like phase change memory and other types of memristors and those kinds of things. Bring those to market, effectively package them on top of a processor, right? Or basically on the right-hand side here, live with the current DRAM architectures and DIMMs on a motherboard kind of approach to supplying memory to processors, in which case we're going to spend a lot more on applications, performance, and stuff. The other thing that we're looking at is, you know, if you have very large vector units, you know, there are applications like DGEM, which is the inner loop of LINPACK benchmark, which make incredibly efficient use of that. But in terms of your run-of-the-mill application, their level of vectorization and efficiency relative to LINPACK is typically an order of magnitude less. And if it's an order of magnitude less, then we have 10 times too much memory bandwidth for that application in terms of delivered flops. So we think we need to change the focus, change the conversation off of LINPACK, because it does, you know, being inside of Intel, I can tell you, you know, Intel, look inside. You know, focusing on LINPACK is what they do because it drives the market. If you're number one on the top 500 list, you sell more systems. And if your efficiency is 85%, you sell more, you know, processors. And then this is the marketing battle that's going on right now in the marketplace. And, you know, we sell processors for a living, so we got to do that, right? However, you know, in this fork in the road, we really need to focus on the real prize, which is predictive simulation and predictive data analytics computations, which means real delivered performance, not LINPACK. We need to focus on performance per watt, and today that's limited by the worst case application, and that's LINPACK, actually. I mean, you know, when I was working in Livermore, you know, we would get about 80% TDP, total dissipated power, of the system running LINPACK. And our run-of-the-mill applications in the you know, the previous generation system was about half that. So we had twice the power infrastructure for the system at its rated TDP, because that's what the electrical code requires, and we would only use half of it. So, you know, when system power was measured in hundreds of kilowatts, who cares? When it's measured in tens of megawatts, each megawatt is $10 million of infrastructure, right? So if I got a 20 megawatt Exascale system, and I plumb it for 20 megawatts, and then actually only use 10 megawatts, I spent $100 million on infrastructure I'm not using. Boy, is that stupid. So that's what that box means. And so on the right-hand side, what we really want to do is actually not sell processors or systems with a TDP, right? That is a number that's written on the faceplate that you take to your safety officer. He checks it. You go to the fire marshal. He says you're good to go, and you have an infrastructure that's based on that number. Rather, you dial it in. It's a dynamic number that you can tell us how much you want to use, right? And this means that when you schedule applications, you schedule them not only in terms of the available node resources, you schedule them on the available power resources, both, right? And I could say, okay, you could have 25,000 sockets and 5 megawatts, which is your limiter? And you say, oh, well, 25,000 sockets, I'm actually going to run at 8 megawatts, so give me fewer sockets so I can go in that. Or change the way that the system is configured so that when I run my application, it's actually running right at 5 megawatts on those 25,000 sockets. So that's another way to think about it. And I think it'll be dynamic, right? And we'll have to have monitoring of the running workload at the system level, both in band for the application to use and out of band for the system monitoring to use, that's ironclad, that guarantees you don't exceed, you know, the facilities limit and blow a circuit breaker, right? That's a completely different way to think about fielding supercomputers, by the way. Completely different. And every time you put a supercomputer in place, you're going to have your safety officer and your fire marshal sign off on the fact that software is going to keep you from blowing a circuit breaker, right? That's a completely different, you know, because the fire guys, they're not on a Moore's Law curve. I don't know if you talk to them. And then reliability, obviously. At these kinds of scales, we're going to have to put in more than just burst buffers that do checkpoint restart kinds of activities into new methods for application generated resiliency mechanisms. So we think there that a new storage paradigm, as opposed to just parallel I/O, is what's needed. So this is a model I came up with at Livermore, thinking about how, you know, at Livermore we were, you know, going to use the ASCII Sequoia machine. It actually is used in two basic modes. One is, dedicate the whole machine to one application, do the science run, but that's only one usage mode. The other usage mode is a quality quantification of uncertainty, or UQ calculation, where you do lots of calculations, because not only do you want to know what the answer is, you know, is the hurricane going to hit Louisiana or not? You know, that's the answer. But you want to know what the level of confidence is in that answer. How wide is the storm path? Is it, you know, 5 miles wide or 5,000 miles wide? You know, if it's 5,000, it's useless, right? And if it's 5, you know which counties to evacuate for that hurricane. Very useful, right? So how do you get that? Well, you have to test the model. You have to test it against a lot of different cases, and you have to test the different algorithms that are in there, the databases of material properties that are in there and all that stuff. That generates a gazillion runs. This is it's an optimization problem over a high dimensional space, which, you know, if you do that brute force, you know, it generates an unbelievable amount of computation. So this UQ methodology is about finding the sensitivity in the application, the cliffs where the answers change dramatically for some reason, so that you know that you're not near that cliff, right, and you have high confidence in your answer. So it requires a bunch of applications running, and those applications all create their own database like HDF5 to manage that data. And basically all the applications and the UQ framework are written in object-oriented languages today. That's Python and C++ and others. And then that then goes into a file, right? That database goes into a file, and that file is transferred across the system across the SAN down to the storage devices by Lustre, and Lustre is actually an object store underneath the POSIX interface. So you go from objects into a database, into a block system, and those blocks are objects, and then on the other end, they're turned back into blocks so that you can talk to a RAID block device on the bottom end. So you know what we need to do in this new storage paradigm is connect the applications up at the top, and the UQ framework up at the top, with the objects at the bottom, right? So that you have an object store all the way through. That's what the Distributed Application Object Store, or DAOS, effort is that we're funded through the ASCII Fast Forward project to work on. So we're connecting the application objects to objects directly on the devices. Then the objects directly on the devices aren't defined by the device, which is what blocks are. It's a device defined storage mechanism. It's the application that defines that. And what that does down there is that those objects stores on the bottom have to become intelligent. That's great for the disk vendors because they're commoditized and their margins are, you know, not very large. So that gives them value. So here's the stack that we're developing. And I mentioned HDF5. That's the end user application library, not POSIX, right? So you can read and write objects that you define for your application through HDF5. That gets translated through middleware to Deos, and Deos transports that for you as your objects to these object storage devices, which actually deal with those objects at the device layer. And oh, by the way, that project, I wired up with some guys out of Intel Labs that were working on big data graph analytics. There's two types of graph analytics, and most people think big data is Hadoop and Hadoop is big data. It turns out it's not exactly the case. A small class of data parallel, highly load balanced, threaded application data analysis like search, and is what Hadoop is. But there's a whole class of graph problems out there that aren't so well balanced. And the canonical example here is trying to find influencers on Facebook. So if you go back and you see something really hot on Facebook, who started that, right? Who was the progenitor of that? Because that's who you want to market to. That's who you want to influence, because that influencer, if you influence the influencer, you influence a community, right? So doing the calculation, it depends on how many people on Facebook like you is your social tree. It's node dependent, and so it's arbitrarily connected. It's not data parallel like on the left, and the amount of computation per node in that depends on the number of people and so that kind of thing is completely different. And by the way, we've layered the GraphLab stuff on top of this HDF5 to utilize Deos to enable these guys to scale up to very large calculations, and they're starting to migrate that GraphLab stuff into a product that is a peer to our enterprise Hadoop product. So a paradigm shift is underway. We're going to move from single thread through frequency and complex architectural improvements to something that has throughput where it's okay, but you get lots of architectural features that help you keep that productivity high by parallelizing your application and directly programming the power and reliability features. So we have some difficult choices here, and this is why we think co-design is critical. We need to make the appropriate trade-offs between power efficiency, what applications can reasonably do to predict their power, and what the system should do for them. The dynamic memory management, RAS, single-threaded performance, that kind of stuff, new storage paradigm, how that actually works in practice. So we're saying that a long-range co-design activity that works on multiple generations so that we can try new ideas, get those ideas into end users' hands, and then learn from that and turn that into the next generation is really where we need to go. And in terms of hardware-software co-design, this is one way to think of the problem. Programming languages, compilers, runtime systems, hardware performance monitors, back into the performance tools, and as I mentioned earlier, we need to collect this data in two ways, in-band and out-of-band. And if the in-band collection mechanisms create load imbalances within an application. And this gets back to what I was talking about earlier, where you really need to be asynchronous in the way that you program your application to handle that load imbalance, particularly when, if you think about it, in a computer room, sometimes you have a hot rack, or it's hotter at the top of the rack than the bottom of the rack, and that kind of thing. So your performance per MPI task is going to depend upon the heat generated and how well it's cooled, right? And so for us, what co-design brings access to world-class extreme scale application experts who are on the forefront trying to solve new problems. And we get from those experts immediate feedback on architectural options. And I can tell you from being inside of Intel, we debate stuff all the time. But when you sit down with an app expert and say, no, that's stupid, no, do this over here, everybody says, yep, okay, and that goes in, right, as a feature. So it's a very powerful mechanism to quickly make decisions, or architectural trade-off decisions, cost-performance trade-off decisions, based on the people who are actually going to use the system and care about it. So this is the real partnerships that we're talking about. And these partnerships require trust, and they require risk sharing. And one of the risk sharing mechanisms that we came up with while I was still at Livermore was, we typically buy these systems to get them at this scale 3-4 years out, right? And who knows how much memory per byte is going to cost 4 years from now. If you can predict that, you can predict the stock market. You should be gambling in the stock market, making a lot more money than being in the HPC. So what we decided to do at Livermore was we say, look, we can't do any better than the market. Make a prediction of where you think the market's going to go, right, and what DRAM is going to cost. And there are very advanced models for doing that. And if everything stays according to the model, you'll hit that number exactly. But if a glue factory in Japan blows up, or we have another economic crisis, all bets are off. You reset the model. So so if the price of that memory goes up or down by 10%, then we'll sit down with you and we'll figure it out. Because if we don't do that, when I was back at Livermore, we decided if we didn't do that, the provider of the technology is going to go, look, if I have to tell you what it's going to cost 3 years from now, I'm going to hedge my bet and put a contingency in there that's substantial, because who the hell knows, right? And if it goes low, I make that as profit, and if it goes high, then I eat into my contingency. So we said, again, we're not going to do better than the market. Just tell us what the number is. If it goes up or down, we'll readjust the budget, how much we buy, whatever. And that actually happened. So we had to sit down and we had to figure it out, and it was painful, but we did it. That's the kind of partnership we're talking about here. And for end users, you get to influence earlier, right? You get to be at the table when the decisions are being made, and that's really important. And so it doesn't always go your way. I mean, the cloud guys want certain things that we don't care about, but at the same time, it's a way to optimize the designs, and if we're going to, which is a thing that we need to do to get to exascale. The other thing is, on these new architectures, we're going to want to explore new algorithms, right? And you want to do that early on so that you can vector the research on the algorithms in the right direction as you're vectoring the architecture to move in the right direction, right? In parallel, you're making these design choices, right? And you want to make sure that you're like this as opposed to going like that. And what that really means is that we need to take application kernels, new algorithms in kernels, and run them on simulators and hardware emulators at some scale, right, that is reflective of the new architecture. And that's a technology we're working on inside of Intel, and we can do that in partnership with the end user customers. So I think our future is very bright here if we can manage it, and if not, somebody else will, because it's required. So so I've been talking about sort of the evolutionary approach. There's also the revolutionary approach, which says, okay, we need to think about computers completely differently. Okay, we need to create a self-aware system that manages its own power, that manages its own reliability, that is asynchronous, that minimizes and adapts the data locality and those kinds of things. So there's also an R&D effort inside of Intel, funded again by DOE, through the fast forward and design forward activities, looking at systems with these. So we think that system components at the exascale will look very different. The processor core will have a very large dynamic range, both in performance and in power consumption. The memory hierarchy will have new technologies, new kinds of memory, and also that the integration of those technologies will be quite different. We'll get on the package and solve those cooling and powering problems. The network will be integrated with the processor and photonics. We're at a phase transition now where we're seeing photonics prices coming down faster than copper cables are going down. In fact, copper cables now are starting to go up in price per bit transferred, which is amazing. So we think a phase-over change to photonics is inevitable. System storage will exploit these new technologies to create a large amount of store on top of a processor and change the B to F ratios back to historical standards. And the programming models will, as I mentioned before, will be moving toward new programming models while preserving the old programming models during this transition, and we'll have both. So the system components will change, but the end user experience will evolve, is our methodology here. And that evolution is a very powerful way to move the very large ecosystem forward in a carefully planned and integrated way. So with that, I'll stop and see if there are any questions or comments. Yeah, thank you.
Mark, I have a remedial question, if you'll forgive the definitional question from the analyst. We start off talking about exascale.
Yeah.
Is exascale a synonym for exaflop? And if it's not, can you give an example of something that's one but not the other?
Yeah. So exascale is a class of systems that have a peak capability measured in exaflops. So it's 1 exaflop to 1,000 exaflop, which is the next generation zettaflop thing. And that's why I talk about exascale systems, because that's 1, 10, 100. And in the petascale era, we started with 1 petaflop-ish systems. We've gone now to 10 to 20 petaflop-ish systems. Next stop is 100-ish, or 1 to 300-ish petaflop systems, and then exaflop is the generation after that. So from that perspective, that class of petaflop systems is, when I say exaflop, is what we're thinking about. It's not just 1 exaflop, it's 1 to 1,000 exaflop, which is really a zettaflop and into the next era beyond. Now,
but exascale is then any system that's an exaflop or up.
Right, in that regime. And it's a 10 plus time period for that band of peak. Now, I've talked about peak. You asked, is it just flops? And I think no. I mean, in the counter example of that, if you look at the big data analytics and predictive simulations, the real metric there is exabytes of data. And so I think it's exaflops and exabytes in that exascale era.
If a system were measuring exabytes of data, but it wasn't an exaflop, would you point to it and say, here's an exascale machine?
Absolutely.
You would?
Oh,
so,
sure.
So really, we're on the verge of exascale now?
Not really.
Well, a lot sooner than the end of the decade, someone could have an exabyte storage.
Well, no, those storage arrays are still pretty expensive. And, they're tens of petaflops. Going to hundreds of petaflops, petabytes, sorry. The storage system will probably cross into exascale before the system does, though. You're right. You're right. And that's why I think the new storage paradigm is a big deal. There's a lot of bytes out there to sell.
Thanks.
Yeah.
What about the FTDF systems how are failures handled?
That's a really good question, and it's a hierarchy. There's low-level circuit failures that are handled, with redundancy in the circuits and better transistors, fatter transistors, and key parts at that level, right? And then there's ECC and other kinds of redundancy mechanisms there. With exterior to that, exterior to the processor, N+1 redundancy is typical. We have RAID 6 and other types of ways to make disks resilient. We're moving away from static RAID things to erasure code, where the RAID is splat across multiple things. So there's lots and lots of techniques applied at lots and lots of levels. But one of the more disturbing things that is, not talked about much in the industry is that our prediction of failure rates and observed failure rates in the field don't correlate very well, right? And the models are not that good. And luckily, we're way more resilient in the field than our predictions would tell us is reasonable. Let's hope that continues.
One final question. Oh, no, again.
Yeah.
You had a slide up that said, if we don't do it, someone else will. That sort of, from one point in your slide, applied an inclusive we versus an exclusive they. Who was the we versus they? Were you talking to United States DOE?
Yeah. That was a we government, the U.S. government versus they, other governments. And
So my follow-up question is, does Intel really care which country does it first? Or do you just want everyone to go for it?
Everybody's got to go for it. Yep. Yep. That slide right there. That's the one. Look, it takes government funding, and there are 3 governments that are in the hunt right now.
Right. In fact, Japan has announced a date. They became the first one to announce a date. They said
Yep.
2020.
Yep. China's got theirs funded in the 5-year plan. The European Union, although they don't have a number 1 out of this list, out of that set, they've got funding to go there too. We're the laggard. Unless something changes in the U.S., it ain't going to be us. It ain't going to be the U.S. And if you want to outcompete, you got to outcompute.
Yeah, I've heard that. One final question.
Yeah.
Can I move it from governments to the other end of the spectrum?
Sure.
That's startups that are early stage.
Yeah.
So is Intel doing anything, or in fact big companies in general, to clarify where they cooperate and where they compete? I've worked with a lot of startups.
Yeah.
Truth be told, some of them are afraid of talking to your company.
Yeah.
Because they don't know whether they're just going to go do it and wipe them out.
Right.
And, so cooperation doesn't happen. And
Yeah.
they're doing cool stuff.
Yep. So I can talk about Intel's approach. Intel's approach is to have a vibrant ecosystem, right? And a lot of innovation comes out of startups. Intel Capital was created to do that. And look at laptops. The Ultrabook generation it says inspired by Intel. What that really means was, hey, here's the design. Here's the things we got to go solve. And there was a lot of funding that went out through ICAP to startups and other companies to invest in them to get the Ultrabook technology to the point where it was cheap, reliable, reproducible, all the things you need to build, laptop class products, right? We're doing the same thing in tablets again now, right? And believe it or not, we're starting to apply those techniques in HPC and the big data space as well. We definitely want a strong ecosystem out there, creating technologies, and it's not just hardware anymore either. I should mention that software plays a big role in that and in ICAP's portfolio. Security was probably our first major investment, McAfee, right? Those guys are now more closely integrated, and Intel have blue badges now and everything, but still are a separate company providing those security products. We think there's a lot of value in security. And I didn't talk about it, but there's a lot of value for HPC in security. Secure authentication and authorization mechanisms that scale, you got to do in hardware. Oh, that's good for us because we have those kind of hardware features built in. So, yeah, we definitely want an ecosystem. And I've seen, the predatory practices that you talked about, exterior to Intel, interior to Intel. Once Intel invests in a startup, either hardware, software, new business practice, kind of thing, it becomes part of the ICAP family, and they actually have ICAP days where all of these companies come through and brief, Intel and other executives about their technologies and try to leverage each other to, enhance the return on investment that Intel has made in all of these portfolio companies. So it's actually quite, it's a helping hand in, opening doors kinds of investment strategy that at least Intel has. Yeah.